Okay, so let's begin. Hi, everyone. Last lecture. Today we are going to, today, hopefully we're going to get to that. It's the most interesting, I think, lecture, like by far, but we'll see. And even if not, we have cookies for the break. I wasn't sure if there's going to be a wave back of people or less. So I can keep one, I guess. Okay, so let's start. So last time we talked about powers of function fields. I'm not going to go back over everything because we have something more interesting to do. But essentially, a tower of function fields is just a sequence of function fields. Each extends the previous one, kind of with a new variable in a sense. And it's not degenerate. Namely, they are actually getting larger and larger. They are not the same. The genus grows. And we saw that once the genus goes beyond one, like it's two or more, then it actually goes to infinity. And we do want the extensions, like each consecutive extension, to be finite and separable. And we proved some stuff. Don't worry about that. But what is important is these three parameters: the splitting rate of the tower. So like calligraphic F is this tower of function fields, which essentially tells you how many rational points do you have at the limit when you compare it to the degree extension. Right, and same, you define the genus or the limit of the genus in a sense to be the same thing, the genus of the ith tower compared to the degree extension. And what is important for us is actually the ratio between these two limits, which by itself is a limit because everything is monotone and nice. So the lambda of the function field tower is the limit of n over g, corresponding n over g's, which is also the limit of the ratio of the limits. And we want this number, if you remember when you did the AG code, when you looked at GOPA code, this appeared in the inverse, like reciprocal to that, g over n, and that was how much you lose. Like the distance plus rate, relative distance plus rate, was 1 minus the inverse of that. So we want this number to be large as possible for the given, or maybe I should have said for the given FQ. Right, all function fields here share the same. I mean, hopefully they share the same. That by definition they share the same, constant field. Okay, yeah. So so we want lambda to be large, particular not zero, and okay. And then we said that the best thing we can do, and indeed there is a typo. It should be a floor and not a ceiling from last time. Yeah, sorry about that. So the best you can do asymptotically, we said that last time, is this expression of n over g, you want it to be large, but it can't be larger than square root of q minus 1. So the inverse of that is 1 over square root of q minus 1, which is what we are going to lose, optimally. And what we are doing now is trying to construct towers that meets this bound. Good. And to do that, we talked about two things: the ramification and splitting locus, actually starting with the splitting. So the splitting locus, just a reminder, it was, all of these rational, the one here is rational, all of the rational prime divisors at the base function field F0, which always split. The split is exactly the degree of the extension. We like those, they give us more and more rational places. The ramification locus are all divisors, not necessarily rational. All divisors could be like hidden divisors of higher degrees, which at some point ramifies. So like if you draw the picture that we always draw, then at some point the E of some edge is going to be more than 1. These are bad, we don't like them. And it's not fun that they can hide above prime divisors which are not rational, because we only care about rational places, but this affects the genus and we have to kind of dig them up and find them. If you saw the more elaborated example, this was interesting actually. There was a weird degree 2 divisor that ramified after 2 or 3 places. Floors. Anyhow, so we want the splitting locus to be large, we want the ramification locus to be small. And then we did stuff, well, actually mostly stated stuff, some calculations. But then we arrived to this corollary, which is nice. It tells you that if you have a tame tower, which means that the ramification is never divisible by the characteristic, which happens if, for example, the degree extension is smaller than the characteristic. That's good. And assuming also that the initial function field is the rational one, but that's always the case, then in that case, I can tell you, in a more less abstract way, what is the splitting locus size, at least, and what's the size of the ramification locus. So the splitting locus is exactly the split size, the size of the split set. So you have to find it somehow. And this ramification locus size is just, just sum up the degrees of all ramified places. All places at the ramification locus that at some point ramify. Once you have these two numbers, and in the example we are going to have those two numbers, like 4 and 6, anyhow. But once you have these two numbers, then the formula for bounding it is actually very simple. It's like 2s over r minus 2. So in this sense, you can also see that you want many places to split. You want this to be large. So many places to split and few places weighted according to the degree, but a few places that ramify. And these are bounds, by the way. They're not necessarily tight, but in our example, they're going to be tight. Asymptotically, yeah. So, okay, so there was some more words and proofs that I didn't say. Actually, these are not completely trivial proofs. We don't have time. And then we define the notion of a recursive tower. This is just a special case, which makes a lot of sense to look at, in which all of the floors look the same. Namely, use the same functional equation, the same f of xy equals 0 for all floors. In particular, we also kind of look at a special case in which the functional equation separates y and x. So f of y equals h of x. So the y is the new variable in a sense, and x is the old variable. And you kind of generate these. And so this is a recursively defined tower. And this was our example. I think we stopped almost after that one, slightly after that one. So this is an example in which you have a function, like an equation. It defines the tower because you add every time a new variable that has this relation with the old, the last new variable that was added, xi and xi minus 1. And I didn't show any of these, but these are easy to show. This is indeed a tower. The function fields grow, they are separable, they are Galois really, but they are separable and so forth. So this is a good example that we will analyze. Yeah, it's more work than what I said. And I think there is also a little bit of a typo here. This is not, you don't care, but this is not 4, it's 6, so it's at least 4, and that's what I needed here. In the example I actually computed that exactly, it was 6. When last time I gave the course, I thought it was 4. And this time, like the night before I gave the lecture, I just kept programming to see that I'm not wrong, because no one ever checked me. And I got 6, like in 2 different ChatGPT generated codes in different languages. So I wasn't sure who to trust, like myself or ChatGPT, and he was right. So it or she, or I don't know, was right, and it was 6. And the issue was that there is a degree, a non-rational place above it, there is ramification, and I didn't think about it. Even though I know it, but I didn't think about it still. Ramification can happen even if above places you don't care about. So it's 6 and not 4, but that's a lower bound, and that's okay. Yeah, never mind. It was a long night. Yeah. So, right. So the last thing we talk about is the splitting locus in recursive towers. So the reason we like recursive towers is because you only have to understand one function field, and it will kind of induce the behavior of the entire tower. And what we said was, if you have a function field with this relation, a recursive function with this relation, and you can find some set of like rational places, including infinity. You don't have to look at the infinity because it may confuse a little bit, but maybe including the infinity. And that set has the property that, first of all, alpha is nice, namely P corresponding to alpha splits completely. You want many things to split completely. So if alpha at the base level kind of splits completely, but I don't know if it will continue splitting, like generally, but this will make sure of that. So the second item tells you essentially that everything above alpha also splits completely. So it tells you that for every prime divisors above this one, and all of them are rationals because they are split completely and so forth. Then when you're going to evaluate your new variable at that thing, you're going to get an element in FQ or infinity if you extend your arithmetic. Don't worry about that too much. If that also belongs to sigma, if that also belongs to sigma, then you would imagine my wife know I'm giving lecture right now, right? Okay, anyhow. Oh, maybe it's an emergency. We'll see. Right. So yeah. So if the evaluation of y also belongs to sigma, then you kind of imagine if you're going to split continuously and so forth like that, kind of a closure property. So once you found a set like that, you're happy because the splitting locus has size, at least that set size. And the proof is not easy, actually. It's kind of funny. When you think it's easy, you think like, what's the deal if it splits and then it continues splitting, then that's fine. But actually relating like different levels of the tower and the base level requires some transporting places here to places here, which is non-trivial. It's like a little bit of Galois, not a little bit, actually. You see, it's like the pictures and stuff. So, but I do want to put it in the videos, but you don't have to see it if you don't want. But I think it's intuitive. And the second thing that's about that I think this is where we kind of stop. The last thing is I tried to look at the previous claim and write it in a operative form. Like, what do you have to do to find sigma? Like, don't talk to me about betas and p's. So this is what you have to do. You can like give it to your favorite engineer and you will understand it. So if you have a recursive tower defined like that, don't worry about m is just a degree. And assume you can find a set sigma, that's the sigma, our sigma, such that but you see not infinities. I don't mind the infinities, I'm going to give one away. Such that for every alpha in sigma, first of all, h of alpha is not infinity, well defined, you can evaluate the right-hand side there. But what's more important, that's just a sanity check. But what's most important is once you plug alpha to h, you get a fixed element in fq. And now you want to solve for t, the equation f of t equals h of alpha. Right, f has degree m, whatever degree we denoted by, but some degree. So it has m roots at some algebraic closure, not necessarily distinct, but if it has m distinct solutions, all of them not only are in fq, but actually in sigma, then you're happy. Because it means that all of those alpha that you found, the sigma that you found, corresponds to place that splits completely. And it makes sense because you plug alpha, you have m solutions, so it splits completely. And when you plug alpha, and it's in sigma, so you can kind of reiterate that. And I think the proof we didn't do, but I think we did the example. Maybe that's where we stopped. Yeah. So that was the example that we did. I'm not going to do it again, but it's a very easy test to do. Any questions so far? It was a 12-minute recap. I just want to look at the message to see, usual problems. So, good. So yeah. So let's talk about the ramification now. Maybe I said a little thing. I'm not sure I even said that, but I'm going to do slow. I'm going to go back to being fairly slow now. So let's say again you have a recursive tower. Now I'm looking at the ramification, not about the splitting. And I'm going to define this set. It's like the analog to sigma. So this is the set. Actually, I don't know what the name of it. I forgot the name. It's like delta or gamma? Gamma? Gamma is lambda. Yeah, none of those. Yeah, thanks. Yeah, gamma is like the hanging. Yeah, lambda. Good. Yeah. Okay. I don't know why ramification is like R, but maybe locus. Okay. So lambda 0. So what is lambda 0? So essentially what you're doing, you're looking at all prime divisors, all divisors, not necessarily rational. All divisors, prime divisors in the rational function field, essentially, irreducible polynomials. Yeah. You look at all of them, and this lemma is under the assumption, that's why I can confuse for a second, so you can extend this lemma, but I don't want to be too general, that all of the ramification occurs over rational places. It's not always the case, but here in our example, it's going to be the case. So I'm kind of assuming, right? Assume that, So I'm assuming that this set delta, whatever lambda, whatever it is contained, like it consists only of rational places and infinity, which is also rational. And this set is, what happened when you evaluate, like it's the name of the prime divisor that ramifies, right? X of p is the name of it, like p of x minus alpha, we call it alpha also, which is the evaluation. So you look at this set, and what I want to say is that these are all the ramified places. Like before, I wanted to say that sigma is sigma or sigma 0, whatever was there. Yeah. So I'm taking it too far away, but here I wanted to say that, once you are split at the base level, you always split, but that's not true. And same goes there. If you are not ramifying, it doesn't mean you're not going to ramify. So I need some closure over that as well. So in that ramification context, say you have this set. These are all the ramifications that you can spot in your eyes. And let's say that you have another set. It's going to be larger. This is the closure in the sense of lambda 0. Let's call it lambda. And it has the following property. So for every element in lambda is also consists only of rational, like prime divisors or elements in the field, base field. If you're going to plug beta to F now, not to H as before, actually, to F, and you're going to solve for alpha, the equation H of alpha equals F of beta, it's the inverse of what it before. Before we plugged things to H and then solve F of whatever. Now we are plugging things to F and solve for alpha in the equation H of alpha equals F of beta. So you solve this equation, it's going to be, there are roots in some field extension, like it could be repeated roots and so forth, but there are roots, including infinity if you extend your arithmetic like we did at the beginning of the course. But anyhow, assume that everything is very nice and that all solutions are actually also in lambda. So lambda is closed in that sense. So for every element in lambda, when you feed it into F and solve H of alpha equals that, also the solutions alpha are in lambda. So if lambda has this closure property, and it contains all the ramified places, the rational ramified places, then what I can guarantee to you is that the ramification locus, which is bad, we want it to be small. As I said, we want it to be contained in something. Then it is indeed contained essentially in lambda. This is a weird way of writing lambda. Like, I was too formal here. I mean, here I should write places, and lambda is elements in FQ. So I translated alpha to x minus alpha in this way, to the place corresponding to x minus alpha. You should just think of it as ramification of F is a subset of lambda when you identify rational places with the field, corresponding field elements. So you want something like that. That's actually even less trivial. It's not trivial at all. Some of the things that you're going to do in the projects will cover that. It's actually, it uses something that's called the, where is it? The name, yeah. I don't know how to pronounce the name, but Yakanharnema or whatever. It tells you something about, if you want to understand places in some extension and you can break it down and you know something here, then you can figure out something there. It's not trivial. But anyhow, if once you have this lemma and like an hour more of Galois, then you can prove that claim or lemma. So I'm not going to do that. Last time I did it, it's in the videos of the previous course. Also here in the slides. But anyhow, let's just continue with our example and see how it operates. I just want to give you the kind of flavor of how things really operate there. So again, the same example, but now I don't know if last time we fixed our field. Let's consider the field F9. Maybe it was last time also F9, I'm not sure. And I'm taking a representation of F9. Yeah, it was. Again, I'm taking a representation of F9 to be, F3 when I add a kind of an I, a square root of -1. Delta square plus 1 is indeed irreducible over F3, so that makes sense. And once you have that, then the equation that we had, which is y squared equals x squared plus 1 over 2x, you can factor the x squared plus 1 because you have an I, which is called delta here. So it's x minus delta, x plus delta in the numerator. And we know, I had this weird assumption that the only ramification occurs over rational prime divisors, which is usually not the case. But here it is the case because that's a Kummer extension. Y squared equals some bunch of like a rational function of, and I identify the irreducible polynomials there, irreducible factors there. And Kummer tells us that the only ramification occurs when this is in 0 or infinity. So that was a theorem that we proved actually. It's a strong theorem. Usually you don't know where the ramification is. My mistake last time was, if I can say, just, I knew that, and we had 2 levels, we have many levels, and I thought, if it works for one level, it works for all levels. But the extension from F0 to F1 looks like that. with y and x. The extension from f1 to f2 looks like that with z and y, but the extension from f0 to f2 doesn't look like that. You can write it down. If you know what the relation between y and x and what's the relation between z and y, you can write a relation between z and x. It's going to be a degree 4 polynomial. It's going to be complicated. And it's not a Kummer extension anymore. So that was my mistake. It was a really subtle mistake. Not proud of it, but I'm okay with it. Anyhow, so we have this equation. And we know that delta 0, lambda 0, the place of ramified places here, by Kummer's theorem, are precisely where the right-hand side has issues, like zeros and poles. So it's at 0, because the pole, plus minus delta because of the two zeros, and also infinity. Why? Is it a pole or a zero just for fun? It's a pole, right? You have two x's above and one x below. So you would hope maybe that's all. Like these are all the ramified places. This set, in a sense, contains this. These are all the ramified places, but it's not. So let's see why. Let's see, you do have to close it somehow. So why? So the lemma that we didn't prove, which uses many things we didn't prove, that's too complicated to do, actually. This would take too much time anyhow. So the previous ones I could have done, but that's not. So it told us that what you have to do in order to be happy with delta 0 is to make sure that it's closed in this sense. Namely, I should take any of the 0 plus minus delta infinity that I had, plug it to f, solve for alpha in h, and hope that the result will also be like that, like 0 plus minus delta or infinity. But that's not going to be the case. So let's try it out. So this is my hopefully ramification locus, but it's not. And what I claim, okay, we'll see why, but I claim that you need to add plus minus 1. And then you are fine. So why? So let's do it. So let's pick some beta, like this one. The lemma told us we should plug it into f. So in that case, it's just f of 0, like y squared, 0 squared of 0, which is 0. And the right-hand side, it's h of alpha, which is this thing. And I need to solve for alpha, this equation. And when you solve it, you see you have a delta minus delta, and that's it. These are the solutions, right? Delta and minus delta, which are actually okay because they are in lambda 0. So 0 actually didn't, 0 kind of was closed in a sense. 0 went to plus minus delta. But if you are going to plug, that's a recap. So if you are going to plug plus minus delta, for example, so what would you get? So f of whatever is whatever squared. So f of plus minus delta is plus minus delta squared, which is just minus 1. So that doesn't matter, and that's I. And on the other side, you have h of alpha, which is this thing. So you need to solve this equation now. So you look at it for a second, move things around, and you see, oh, it's actually alpha plus 1 squared. Right? And so minus 1 kind of, it's not close. You need minus 1 also in that set. So you add minus 1 there. And when you add minus 1, so if I plug minus 1, forget about the plus 1. If you add minus 1 squared is 1, and you solve now again for alpha, you see that you also need 1. So 1 should be there. So I also checked 1, like to save space. And that's fine because 1 goes to 1 as well. And if you check the other ones, I think infinity is interesting. So if you check also infinity, so you again, with the extended arithmetic, infinity squared is infinity. It looks like a weird thing, but it's okay. Which is h of alpha, which is this thing. And if you want to solve alpha squared plus 1 over 2 alpha equals infinity, there are two solutions. Well, infinity, because this has a polar infinity, and 0, because this is not 0 at 0, and this is. But these are also in lambda, so you're fine. And that's the set that you have. So good. So we know that what the ramification locus is contained in that, and actually it's equal to that, because these do ramify. You can see that if you look at the picture that we had. And the splitting locus, if you remember from last time, we had 4 prime divisors that split completely, like 1 plus delta, 2 plus delta, 1 plus 2 delta, and 2 plus 2 delta. So we know that S is at least 4. We know that R is 6. We have 6 divisors here. All of them are degree 1. So the sum of their degrees is 6. And so according to the theorem that we had that kind of closed everything together, kind of this forgot the name. This is also lambda. Another lambda, yeah. So good. So the lambda of the tower, oh, that's why maybe, okay. The lambda of the tower is 2s, at least 2s divided by 4r minus 2. You know, you can calculate it, it's 2. And then you can ask, is 2 good? Like, do you like the number 2 for this tower? And you very much do like this number. Because the best thing you can do is square root of the field size minus 1. That was like the theorem that we are going to start talking about today. That's the Hasse-Weil bound, or like in its limit, like the yeah. So that's Ihara's constant. It's called like square root of q minus 1 is the best you can do. This is square root of q minus 1 is q9. So that's actually an optimal tower. That's a fantastic code. Like that curve, if you're going to instantiate it with Gopa codes, it's going to give you a fantastic code over F9. Good. So, you know, you can ask, what about if I change q to some other number? The same tower, but don't work over fq. So it turns out that it's an optimal tower for every q that's not even. And it's an even power. Right? So for every prime that's not 2, and any even power of that, that's going to be an optimal tower. It's going to give you an optimal tower. That's amazing, because that's almost the simplest equation you could imagine. Like, you know, it's like 2 parabola. Like, it's very simple. And so what do we need to in order to prove that? Well, you know, it's going to be like maybe somewhat underwhelming, but I'll tell you a word about it. So first of all, it turns out, I don't want to do it again, but it turns out that the fact that R is at most 6 is R is at most 6, what we did now, the ramification locus, that calculation that we did actually has nothing to do with F3 or anything like that. You can do it for every, not just for 9, sorry, for every prime power which is not even with an even power, whatever. That's simple. The hard part is this 4, right, the splitting locus. So what you can do, I mean, okay, so what I'm claiming, but not proving, is that the splitting locus is actually 2 times p minus 1. Right, so for p equals 3, I mean, the q was p squared. For p equals 3, you get a 4, but generally it's 2 times p minus 1. And for every particular p, you can just check it. It's not so hard to find the splitting places, like, according to the lemma that we had. So if you trust me for a second that you can check for every p, I mean, no, you can't trust. If you trust me that if you check for every p, then that's fine, then indeed lambda is going to be optimal, because it's going to be, well, you know, 2s divided by 6 minus 2 all the time. The 6 remains a 6. So 2s divided by 4, which is s over 2. So lambda is going to be s over 2, which is p minus 1, because s is 2p minus 1 if you trust me, and p is square root of q, optimal. Okay, so what this tells you is that if you just check your favorite p, like p equals 7, and you just find the 7 places that split, and it's not hard to do that, actually. For every particular p, you know exactly what they are. When you can actually show that these are optimal towers, and that's amazing, because they are very simple, degree 2 extensions like that. If you want to prove it generally without doing it p by p, then that's difficult, and it's beyond what I know, actually. I know what I need to know, but I'll tell you, but I don't know a theorem, a proof of a theorem. It's not so easy. So it turns out, and let me just tell you one thing about it, that the key to actually prove that the splitting locus is 2p minus 1 for every p, like not just for different p's, is to look at this polynomial, which looks like someone just like threw up a polynomial on the slides. So, and that someone is During, so it's good for up. So it turns out that for every p, you can look at this polynomial, which comes up naturally in some settings. Yeah, you can stare at it for a second. I don't have anything like very smart to say about it. But I just, you know, to give you a sense, this is H3 that we talked about. Like P is 3, Q was 9. So our polynomial, the hidden polynomial that we kind of used was 1 plus x. And generally it will look like that. H5, H7, and so forth. And what you can show about this polynomial, and that's not easy, is that it satisfies some functional equation like that. So it turns out that that polynomial when you plug in x as polynomial equations, not just like equality as functions over FP. Like this is the same polynomial, stronger thing, right? So HP, when you plug in x4, x to the fourth, is actually x to the p minus 1 times the same polynomial when you plug in like the thing that was used for constructing the tower. That's where it came from, actually. And that's fantastic. That's very weird. It doesn't look like you have a 2 over x. It doesn't seem right. Like something is wrong, but it's okay. I checked here just x3, but because I didn't kind of believe it and checked all the time. So, but you don't worry about. I just checked it for myself for h3. But that's an equation that you have. That's hard to prove. Okay, I don't know how to prove it in like elementary ways. But if you know that, from here it's kind of easy to continue, because once you know that, that's also not easy. It's like a different homework assignment that I'm not going to give. But what you can show is that lambda 0 that you care about is all of the alphas, such as when you plug alpha to the fourth in this polynomial, you get 0. Don't worry about it. But from here, there is a very easy way to derive lambda 0 and lambda afterwards. And that's the thing I'm not talking about today. But what we have done is that, what we have done is prove what I did give you, besides for some proofs omitted, is indeed optimal function field, optimal tower of function fields, which will give you optimal codes in the AG code sense. Now, in the projects, you're going to look at other optimal towers, which look something like, okay, I'm going to mess it up now. So you're going to look at this example. Actually, with minuses, this is what appears on the cover of the book that we have, the Stichting book. I like the pluses more, just because this is the norm. I think it should be like that. No, that's fine. This is the trace. Oh, yeah. And that's the norm over the trace. I mean, you need to multiply by x both to get the norm over the trace, but it's the same. It's just kind of, and this is the Hermitian function field that we talked about, and this is the Garcia-Stichtonov tower. The Hermitian function field is great, but it's very poor as a tower for constructing codes, and this is going to be optimal. And you're going to prove that it's going to be a harder task in a sense and a weaker task in a sense. It's going to be harder because these are not Kummer extensions. These are called Artin-Schreier extensions, which are harder to understand. I actually did all of them like in the previous course, so you can also look at that if you want, but also on the projects, you will see those, who is going to do it and those that are going to choose to come. So it's harder to do, but once you do that, you don't have to rely on like even deeper results that I don't know to explain much. Okay. And in the tutorial today, in the recitation, Tomer will show you another optimal function field, like very different one. Good, so that ends this part of the course. Like we are going to move to the zeta function now. Any questions so far?